this here. All right. Okay, so I posted another Moodle assignment because they're so easy for me, and they make you work a little bit, and that's what assignments are all about, right? So anyway, so assignment number 6. Is a Moodle quiz. Well, and it is due, I want to say next Thursday. Is that the 21st? Due November 21st. Thank you. At basically midnight, 23:59. Great. So today we're gonna keep going with trig, sine, and cosine, kind of the foundations. Spoiler alert, we're graphing today, but not too bad, because as you probably noticed, there's usually kind of like a shell formula, and then as long as we can match our formula to that, it's easier to sketch graphs, right? So we're gonna use that mainly. Okay. Before we do that, we're gonna finish the last example from last day. Where's my, oh. So on the handout from last day, the one with the globe on it, we finished off and we did example 10.2.5, just keeping the numbering from the textbook. So now today I want to talk just briefly about equation 10.3, and then we'll do a quick example and that'll be good. So 10.2 handout. Suppose an object is traveling in a circular path. So we've been talking about circles for 2 days now. May as well keep going. Right, so in a circular path of radius r, centered at the origin with constant angular velocity omega. If t equals 0 corresponds to the point r0, then the x and y coordinates of the object are functions of t and are given by x equals r cos omega t and y equals r sine omega t. Right? So very similar to the formula that we, the formulas that we established last day, where we incorporate any radius r. Right? And so now we're just throwing in an omega and t instead of theta. Where omega is greater than 0 indicates a counterclockwise direction, and omega less than 0 indicates a clockwise direction. Good. We can jump right into an example. Suppose we're in the situation, that's not very clear, but luckily you've got that blurb, and that's the example that we did last day, right at the beginning, where we said, okay, well, we've got Earth is a sphere, and then we had to find the linear velocity in miles per hour of Lakeland Community College as the world turns. Okay, so we're at Lakeland Community College. We know the angular velocity, we know the linear velocity from the example that we did last day. And so Now we want to find the equations of motion, which are just x and y. So we know that the radius at this point was 2,960. Also because that's where we ended off last day, and we said a good approximation for the radius at Lakeland Community College was 2,960 miles. And we said, and this is from last day, that omega, if I can do a nicer one, sort of, omega was 2 pi. So this is the angular velocity, right? And so we've got 2 pi, that's the distance. Over time, it takes 24 hours. Which, if we simplify that, we get pi over 12 hours as our omega. So if we know r and we know omega, we can leave t as a variable, right? That's fine. So now we can solve for the equations of motion. We can now solve for the equations of motion. X is r cos omega t where r is 2960 times the cos of omega, which is pi over 12, and then times t. T would be in hours. Pi over 12 is actually pi over 12 hours, but those hours would cancel, right? And so then you're just taking the cos of a real number. So, we can't simplify that. That's it. And then y, and y has the same format, r sine of omega t. R is still 2960, but we want sine of omega t. Omega is pi over 12 times t. Clean that up a bit. Should extend my brackets, I guess. Where x and y are measured in miles, and t is measured in hours. So if I ask you for the equations of motion, right, then you use these formulas, right? X is r cos omega t and y is r sine omega t. But then it's not so bad. You just have to find r and omega, plug them in, and then you're done. Any questions about that one? All right. Then let's get into 10.3. 10.3 is graphs of sine and cosine. At the very least, you probably know that sine and cosine look something like this, right? And it goes on and on and on. Oh, not like that. Right, so probably know that it looks something like this. Got this wavy motion. So specifically, we know, and I'm going to assume this, that the start of our graph matters. For sine, it starts at the origin, and then we go up and down. So if we have sine of x starts at the origin, and that means that cos of x, made it too big. Cos of x starts at 1. And cycles through. Right. So here, oh, I guess I should label it. This would be cos of x. So sine of x starts at 0, 0, whereas cos of x starts at 0, 1. Thanks. I used to remember it that they appear alphabetically, C before S. I don't know, whatever you have to do. Or you can just memorize it. Which one starts where? Just some general facts. Both sine x and cos x, both sine of x and cos of x are bounded by y equals -1 and y equals 1. Right, so we're never going to go beyond 1 and -1. Are bounded by y equals 1 and y equals -1. Therefore, their range is going to be from -1 inclusive to +1 inclusive, because it's allowed to be 1. And since these things are cyclical and they're going to keep going forever and ever and ever, and they never taper off, they just hold the same shape forever, their domain is -infinity to infinity. So, and since these functions are cyclical and never end, the domain is negative infinity to infinity. These and other facts are summarized on the handout I gave you today in theorem 10.5. But first, I guess we'll do definition 10.3. It's just talking about periodic functions. So a function f is said to be periodic if there's a real number c, so that f of t plus c is the same as f of t, right? And so the output of f of t plus c is the same as f of t. So as you move through your cyclical motion, right, at some interval, you're going to end up at the same y value, right? And so for all real numbers t in the domain of f, the smallest possible number p for which f of t plus p equals f of t for all real numbers t in the domain of f is, if it exists, is called the period of f. So the period of f is just how long does it take to get the same output, essentially. In this case, if we're talking about cos of x, for example, right, the output here at our starting point would be 1, right? Cos of 0 is 1. And so it would take us that long to get back to a y of 1, right? Or a cos x equals 1. So that's the period. Since the sine and cosine of angles are coordinates of points on the unit circle, right, which we talked about last day and the day before. Since the sine and cosine of angles are coordinates of points, on the unit circle, we know each revolution is a period of sine and cosine. That's how long it takes us to get back to that same point. We know each revolution is a period of sine and cosine. Therefore, they have a period of 2 pi. So P, we would denote is 2 pi, lowercase p. And kind of unrelated, but I went to the program advisory committee for the wet department last night, and I was talking to Frank, and I was like, oh yeah, he said, oh, what are you guys doing? Oh, trig, oh, that's great. And then he said, make them memorize the unit circle. I said, you got it, Frank. Your wish is my command. So we'll see what we can do there. Kind of hard to make you memorize it when you have to make your formula sheet, or you get to make your formula sheet, but probably a good idea to have it under control. Because he does, he touches on calculus later with you guys, right? So a little bit. But it sounds cool. So what we noticed, right, was kind of the same idea as when we talked about the unit circle, right? We said, okay, well, we can boil things down to just one quadrant. Same idea, as long as we know how one, oh, sorry. Yeah. And this one. As long as we know what one cycle looks like, then we know how the rest of the cycles behave, right? Because they're just going to replicate over and over and over again, just moving over by 1 period or 2 period or 14 periods or whatever. Okay. So we can therefore understand everything about the function. We can therefore understand everything about the function sine x or cos x sine x or cos x by studying one interval of length 2 pi. By studying one interval of length 2 pi. Let's have a look at theorem 10.5, this little guy here. Copy. These are just kind of good to know and good to have summarized, but would take us forever to write out, so we don't need to. So properties in general of cosine and sine functions. So sine and cosine both have a domain from negative infinity to infinity, which we established, a range from -1 to 1. We also established that. Just as a fact, they're both continuous and smooth, meaning there are no asymptotes or no discontinuities or anything going on like that. And then sine of t is odd, and cos of t or x or theta or whatever, cos is even. And they both have a period of 2 pi. So what it means to be odd, mostly just for completeness, not because it's important, means that the sine of negative t equals the negative sine of t. Whereas if you have an even function, just in general, then the cos of negative t is just the cos of t. So that's just what it means to be odd and even. It's not terribly important, but completeness, right? So if the name of the game here is to sketch a sinusoidal function, so that encompasses sine and cosine, before, right, when we were sketching functions, we would trace points, right? We would pick some key points and then we would trace them and follow them until we ended up at the final graph, right? That is one way that we could do it. And for that, we use what we call a fundamental cycle, which is also on your handout. I'm going to give you one of those, well, if you flip the page, I guess, you'll see that there is a general formula for how to graph sine and cosine functions. But we'll get there. And so, it might be helpful to know some key points on the graph of sine and cosine. I'll just do sine of x and cos of x. They've got t on the handout, but it doesn't matter. On the graph of sine x and cos x, if we have to graph them. We make use of the quarter points or quarter marks on the fundamental cycle below. So here, well, not below for you, I guess, on the handout. So for graphing, what we'll find is that we split our period into quarters, right? Because at each quarter point, there's going to be a change in the graph, right? And so the first part is 0, 0 for sine of t, and then we've got at the quarter mark, we've reached the top, and then at another quarter mark, we're back down to the same y as we started at, and then next quarter mark, we're at the minimum, and then we're back, and we've completed a complete cycle. And so these are called quarter marks. Those look like they're from the unit circle, right? All looks a little too familiar. All right, we've got pi over 2, pi, 3 pi over 2, 2 pi. And then we just go around and around the circle. Same thing with the cos. Remembering that sine of t on the unit circle, right, that was our y coordinate. Cos of t, that would be our x coordinate on the unit circle as we move around, right? So we start at 0, 1, and then we move to pi over 2, 0. Let me cycle through. Question, Andrew?
Is it always going to be going counterclockwise to the right of the graph, on the right side of it, 0? Or does that just tell you that it's negative positive?
I'm not sure it matters, actually. But I'm pretty sure we're assuming that we're moving counterclockwise, so our angle is positive. Mm-hmm. All right, so these are just the fundamental cycles, and so these quarter marks are worth kind of committing to the old noggin or your formula sheet, whatever you do, okay? And so, all right, but it just maps the general behavior of one cycle of sine and cosine. All right. Sinusoids, which I'll define here, sine and cosine, right, in general, can be characterized by 4 properties. Can be characterized by 4 properties. First one being the period. Because what we'll find is that these graphs are rarely going to be nice and clean and just looking like the default, right? We're going to transform them a little bit. We're going to squish them, stretch them, do whatever we want. But in general, they're all going to have some period. They're going to have a phase shift. So the phase shift is just how far to the left or to the right has this whole kit and caboodle moved. Third one being the vertical shift. So how much has it shifted up and down, or up or down? This is also called the baseline or baseline. And the fourth thing is the amplitude. How big is this? Are these waves? Wait. And you've got just a general graph mapping out what these things are on this curve. Right, so the amplitude, one thing to notice is that the amplitude is only from the baseline up to the maximum or the minimum if you want, but then you'd have to drop the name, right? And so the distance between the baseline and the maximum, that's your amplitude. And your baseline is that center line, right, which would be affected by a vertical shift, and so that's why it's the vertical shift. If you've moved up from y equals 0, for example, then you would have a vertical shift up. And then the period is just the distance from start to finish of one cycle. And the only thing that's not on here is the phase shift, is the distance that's been shifted from left or to the left or to the right. So, and the phase shift is the distance the graph has been moved to the left. I'll put in brackets if negative, or to the right if it's positive. Does not. No, it'll just. No, it'll just always stay from negative infinity to positive infinity. It'll just always keep going. So we can shift them because we're dealing with infinity, right? So it's, you know, you take a little bit off infinity, it just keeps going.
Your quarter marks would change, you know?
They would. Cool. Then let's flip that page for the moneymaker. If we're graphing, of course. Theorem 10.6 gives us an outline of what these things are going to be mathematically. So for omega greater than 0, so we are assuming that we're moving counterclockwise. Moving counterclockwise. The graphs of a sine curve and a cos curve in general, right? And so these are all the things that we could do to manipulate sine of t and cos of t, right? Inside the sine, we could multiply t by some number, and then we could add some number to that, right? That's the extent of things that we could do in there. And then if we move out, we could multiply that sine by some, it turns out it's the amplitude, right? And then we could add some phase shift b. And so here we've got a summary of, so the period of either of these is going to be just denoted by a capital T, which is 2 pi over omega, right? So from your equation, you'll be able to pull out omega as long as you can rearrange your sine or cosine to match this one, right? Then you know that here, this omega is the same omega that goes in the period, right? So then you can find your period. The amplitude is the absolute value of A, right? So as long as you've been able to rearrange your function to match this, and you should be able to, then you'll be able to find the period, the amplitude, even the phase shift. This is a phi. How solid your Greek letters are, but this is a phi, so it's a circle with a line through it, and then you've got omega again. So the phase shift is going to be the negative value of phi over theta, where phi is getting pulled from inside the sine or the cosine, and omega is the same that we used earlier. And then the vertical shift, or the baseline, because it's the b, right, is just that b. Okay. So if b is positive, you've shifted things over to the right, and if it's negative, you've shifted things over to the left. Okay. Where omega is the angular frequency, or kind of from here on out, we'll just call it the frequency, or simply the frequency. The frequency, we've already talked about it, but the frequency is the number of cycles the sinusoid completes over an interval of length 2 pi. Right? And so hey, I forgot a word in here. It's the angular frequency. Well, it didn't make sense. Omega is the angular. What? Or simply the frequency? No, the angular frequency. Or just the frequency from now on. The frequency is the number of cycles the sinusoid completes over an interval of length 2 pi. So if you think about just the word frequency, right? If you have a high frequency, then these things are nice and tight, and this is high frequency, right? If you've got a low frequency, then it's nice and slow, right? And so it takes completes less cycles over 2 pi. Okay. The ordinary frequency is denoted by lowercase f, is the number of cycles, so it's the same thing, but it's just the number of cycles it completes over a length of interval, an interval of length 1. So is the number of cycles the sinusoid completes over an interval of length 1. Mathematically, the ordinary frequency is 1 over t. 1 over t, t is the period. So same idea, it's just over an interval of 1. Oops. The phase, or the phase angle, the phase or phase angle is denoted by phi, and it is the angle in the argument which corresponds to t equals 0. Not terribly important, but just again for completeness. So it is the angle in the argument which corresponds to t equals 0. Right. The starting time point, right? If we're thinking about time, which, okay, fair enough, doesn't really tell us much about what it is, right? But if t is 0 in either of these, then yeah, then you'd have the sine of phi, and so that's the angle when t is 0. But we're not going to get into when we use it or anything like that. Any questions about that before we do our example? Okay. Example. Determine the frequency, period, phase shift, amplitude, and vertical shift of, and then I'll give it to you. Determine the frequency, period, phase shift, amplitude, and vertical shift of, we'll put it on the next page, f of t equals 3 cos pi t minus pi over 2, and then plus 1. And use this information to graph one cycle. And then we're going to finish it off with find and interpret the ordinary frequency So of course, we're going to use theorem 10.6. That's going to give us, right, if we've got our list here, as long as we can rearrange f of t to match one of these equations, right, then we can find the period, we can find the amplitude, we can find the phase shift, and we can find the vertical shift. So that's a lot of what we want. So here we go. We need to rearrange, right, because we need to match the form from the theorem, right? And so we've got a cosine, so of course we're going to match the cosine one. So C of t, so we need to match C of t equals A cos of omega t plus phi plus B. So we rewrite, so we can rewrite, and I'll just write the original formula here to see what we need to do. F of t is 3 cos pi t minus pi over 2 plus 1. Right, we need to rewrite this to match omega t plus theta. That's not that bad, right? I can just split up that common denominator of 2 and rewrite this as 3 cos pi over 2t minus pi. Oh, but I have to have the plus in there. And so, hold your horses here, plus negative pi over 2 plus 1. Now it matches that form where we've got A equals 3, omega equals pi over 2, phi is negative pi over 2, and B is 1. Okay, so we'll just start from the top here. We want the frequency. The frequency, remember, is omega. And omega in this case, oops, we said was pi over 2, right? Just from our equation. Frequency, done. Okay. We wanted the period. The period from the theorem is equal to t, which is going to be 2 pi over omega, which in our case is going to be 2 pi over pi over 2. Keeping in mind that we can rewrite this as a fraction over a fraction, right? And then we can flip and multiply. And so we can rewrite this as 2 pi technically over 1 times, and then pi over 2 flips, and so times 2 over pi. These pi's are going to cancel, and so our period is just going to be a length of 4. Right? So there's a length of 4 plate. Okay. So that was the frequency, the period, the phase shift. Then the phase shift from your formula, or from the theorem rather, probably put it on your formula sheet, is negative phi over omega. And so from our equation, we know that phi is negative pi over 2, and omega is pi over 2. And so we've got, just careful with your negatives, right? We've got negative pi over 2 divided by pi over 2. Now, whether you want to do this the long way or recognize that pi over 2 over pi over 2 becomes 1, that's fine. Or you can just treat them as a fraction over a fraction, which I'll do because it's proper, I guess. We've got negative pi over 2 times pi over 2 but flipped times 2 over pi. I'm going to ditch those brackets, actually. I should have canceled these already. Negative and a negative cancel. It all cancels. Pi and pi cancel, 2 and 2 cancel, and all you're left with is a measly 1. This is positive, right? So that means that we've shifted over 1 unit to the right. Shifted 1 unit to the right, right? Because it's positive. How about the amplitude? The amplitude, well, that's just the absolute value of A. The absolute value of A in this case is 3. So the absolute value of 3 is 3. And then finally, our vertical shift. Vertical shift is B, which in our case is just positive 1. Okay. So now we know that instead of starting at x or t equals 0, right, we've shifted 1 unit to the right. So we're going to start there, right? So our starting point is at t equals 1. So to graph y equals f of t, right, using t on our x-axis.
Does that mean that our graph would start, our lowest point would be 2 if our amplitude is 3?
Pretty sure. Well, our lowest point, because we're starting with cos though. So you have to move over 1.
So it just starts.
No, because we've stretched it now.
Okay.
Yeah, but well, we'll see.
Start out 1 and then there's a vertical shift of 1 and that started. Well, that would go what I was saying is we have an amplitude. But we only have a range of 1.
Yeah, so cos starts at 0, 1, right? And then we've moved it over by 1. So now we're at 1, 1. And then our vertical shift is 1. So now we're starting at 1, 2. But then we have to take into account the amplitude.
So you go up to 4.
Yeah.
Down to -2.
Yes.
Because the amplitude is 3.
We're going to do that, but we're going to do it more structured by making a table of values. So we don't have to do it in our heads. But that is what we're doing. To graph y equals f of t, we know one cycle begins at t equals 1, right? The phase shift. And since the period is 4, we know the cycle ends 4 units after 1, right? So we know the cycle ends at t equals 1 plus 4, which is t equals 5. The exact same thing that you guys were doing, but just kind of more structured so we can replicate it, right, is if we split this distance from 1 to 5 into quarters, right, because we know that, okay, well, one of those is going to be the maximum, the minimum, midpoint, 2 endpoints, right? And so we're going to split this into quarters and then look at what each of these values are at those quarter marks.
We're basically just manipulating the code graph now.
Yeah. To help graph f of t, we divide 1 to 5, the interval from 1 to 5, into 4 equal pieces. Into 4 equal pieces. I'll put in brackets the quarter marks. So we're going to look at t equals 1, 2, 3, 4, and 5, where 1 and 5 are the endpoints, right? And then 2, 3, and 4 are splitting that interval into quarters. So now what we're going to do is we're going to say, okay, well, I'm going to substitute each of these values into f of t, because then even if we don't have something that's as easy to deal with as what we've got, right? Say you've got an amplitude of pi over 6, right? That's not so easy to graph, right? So here it's easy to think of, okay, we've got an amplitude of 3, blah, 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 right? But that's not always going to be the case. And so at least if we've established this method of doing it, then you can convince yourself that it works for all values. So now we can now substitute these quarter marks into f of t to obtain the corresponding y values on the graph. So it's always nice if we can just organize a table, right? T is 1, 2, 3, 4, and 5. And then we can solve for f of t. Well, just to show you once, right? F of t is 3 cos pi t over 2. T is 1 over 2 minus pi over 2 plus 1. If you do this on your calculator, making sure that you're in radians, right? Because we're dealing with pi's and things. And so you've got pi over 2 minus pi over 2. So here, this would simplify to the 3 cos of 0 plus 1. So if you make sure you're in radian mode, and you also know what cos of 0 is, it's 1. But angle unit, just to confirm, you take the cos of 0, you should end up at 1. And so you've got 1 times 3 plus 1 is 4. You could have just done it on your calculator. Make sure you are in radian mode. You would do the same thing for the rest of the t's, right? Just keep substituting in t equals 2, 3, 4, 5, and I'm going to cheat here and say we get 1, -2, 1, and 4. At 1 and 5, we have to end up at the same value, right? Otherwise, we haven't covered a complete cycle, right? So those have to be the same values. So now we can graph this. Okay, so I know I'm going to start at 1, 4, and my highest point is 1, 4. My lowest point is 3, negative 2, right? And so what that means is my highest value of y, right, or f of t is 4, and my lowest value of f of t is negative 2. So I have to make room for that on my graph. So if I've got, using one line for each, I need 1, 2, 3, 4. Nice and big here. 1, 2, 3, 4. Negative 1 and negative 2. Then I'll do 1, 2, 3, 4, 5. A little squished, maybe. But now I can plot these points, right? And so I've got 1 and 4, 1 and 4, 2 and 1, 3 and negative 2, 4 and 1, sorry, and 5 and 4. And because this is sinusoidal, I know that there's some curvature going on in here, right? So I don't want to just make a V here. I want to have something that, oh. That kind of resembles, I didn't do a very good job, but that's okay. We have to have some sort of curvature. Things got wonky right around. Oh. Maybe I'll do them separately. That looks better. Okay. So then finally, so there's our graph. Nice work. Right. And what you'll find is, okay, as long as you can figure out what the interval is, right? So if you know where your starting point is, using your phase shift and then your period, then you can figure out what your interval is, divide it into quarters, and use those marks in your table to figure out what the y values are, and then you can map them out. We were also going to find the ordinary frequency and interpret it. The ordinary frequency is that lowercase f, which is 1 over t, capital T. T is the period, and so f is 1 over 4. I'm going to put this on the same line, even though I shouldn't. But there's a page break coming up, so and I want to squeeze it all on. Therefore, a quarter of the sinusoid, remember how much, so the frequencies tell you, so the ordinary frequency tells you how much of a cycle is completed in the distance of 1, right? Just looking at this and judging by our quarter points, right, we know that it's a quarter, right? And so a quarter of the sinusoid is traced out over an interval that is 1 unit long. Okay. Nice. Any questions about that one?
So you just always have to pick when you're trying to find frequency or ordinary frequency, you always have to pick your first interval.
The ordinary frequency? Oh yeah, for your quarter marks?
Yeah.
Yeah, you'll start where your phase shift starts, because that's going to be the easiest. And then break it up into quarters, right? From the phase shift, add your period, and then break it up into quarters, and those are your quarter marks. So it's a little bit more structured, because before, if we were just picking, different values of x to follow, and then we figure out what the y is, it didn't really matter which values we picked. We tended to pick easy values of x, 0, -1, 1, typically, right? But now we're going to start picking just the quarter marks, because that's where the graph changes from maximum to minimum, etc. All right. Let's do example 10.3.3. So here, we're going to work the other way, right? If I give you a graph, then you can give me the function that would give you this graph, right? So we can work either way. Okay. We're only going to do the first one, and then if you want to practice with the second one, right? Because there's, we're going to do it for cos and then for sine, but just doing it for one isn't. So we've got the graph, and it starts at -1 and 5/2, and then it ends at 5 and 5/2. All right, so first off, we notice that the phase shift must be -1. Right? So we can start there. So if we want this for a cos curve, right? And so here we want C of t equals a cos omega t plus 5 plus beta. Right? For omega greater than 0, but we'll ignore that. We notice, right, this is one cycle, right, that's fine. So we notice one cycle, oops, one cycle is graphed over the interval -1 to 5. So the period is t equals 5 minus -1. Or however you want to find, that's technically how you'd find it, right? The right endpoint minus the left endpoint. But you could probably just look at it and say t is 6.
So if you want vertical shift, is your amplitude still from the 0 to, or still from 0 to 0?
No, it has to be from the baseline. So if you've shifted, yeah, so if you've shifted, if you've had a vertical shift of 2, right, then you would start at 2 for your amplitude. Yeah.
I noticed you could use
Sometimes like they capitalize and other times they're lowercase.
Mm,
Making
it is, yeah. Capital T is the period, whereas a lowercase t would be time, or what we've been using as our x-axis. So yeah, they do. And don't worry, I haven't been mixing them up. I had a prof who would do that and was like, and he'd always get so mad if we were like, do you mean like a capital T? And he's like, well, what? You should just know by the context. We're like, we're.
I think his textbook says one thing. Our lecture notes have something else. We use examples on the board using different letters. 3 weeks to understand quality.
Yeah, and he would get so mad. It's like, you should just know what I mean. Well, they're not all the same. Now I know what he means, but you have to have a good grasp of the material before you can kind of handle stuff like that. So, all right. So we know our period, and we know that our period is 2 pi over omega, right? Our frequency. And so if we know our period, then we can work backwards to find our frequency. And so we know that T, capital T, is 2 pi over omega. And so we can solve for omega because we know that T is 6, which must be 2 pi over omega. Multiplying omega over, but simultaneously dividing the 6 on both sides, I get omega must be 2 pi over 6. So we have omega is pi over 3. Yes.
Okay, so back up. Thank you. How is the interval -1 and 5? They're both x values.
Well, so here
Like, are you not taking the 5 from the far right and the -1 from the far left there?
we are, right? But here they've just labeled our x. We're used to calling it the x-axis, but now it's just trying to push us in the direction of, okay, well, over time, this is how it works, right? So then we replace our x with t. And so that's why we have t in here and in here, right? Because that's our x value.
Okay.
But we can, if we're talking lowercase t, you can just imagine it being x. Because it is just
So then you just
a spot on the x-axis.
How long between each cycle?
Yeah, the distance. Yeah, so that's the length of one cycle is your period. Yeah. Mm-hmm. Okay. We already saw, so we see that the phase shift is -1, right? 1 unit to the left. So if you recall the phase shift, right? The phase shift formula was -phi over omega, right? Just from your formula sheet. Well, theorem 10.6. But I'm hoping it'll be on your formula sheet. At least theorem 10.6. And so, and we also know that this is -1. we can substitute omega because we know what omega is. Omega is pi over 3, we just found. And so then we can say that negative phi over pi over 3 is negative 1. You could cancel those negatives now or leave them till later. I'll cancel them now, right? Divide both sides by negative 1. So then if we multiply pi over 3 over to the right-hand side, we get phi must be 1 times pi over 3. So phi must be pi over 3. So we're just reverse engineering things here. All right. So we've got, what do we know? We've got our period, which doesn't really factor into our equation, right? But we needed it to find omega. So we know our frequency, we know our phase shift, phi, and then looking at the rest of the formula, we need A and B, right? And so we can start with B. We have to start with B actually. So you'll see why in a sec, or maybe you already see it. To find the baseline, we recall that the baseline must be the midpoint between your maximum and your minimum values. Right? Must be the midpoint, of your maximum and minimum values. So we can take the average. We can take the average of max and min to find B, the baseline. Drop the baseline. B, if we're taking the average of the maximum and the minimum output values, right? So not your T's, but your X's, but your Y's. Then if we look at our graph, right, we're told that the maximum output value is 5 over 2 and the minimum output value is negative 3 over 2, right? And so those are the values that we're going to average. And so we've got 5 over 2 plus negative 3 over 2 divided by 2, right? That's how you would find the average of those two values. And we're not scared of those fractions anymore because we've done so much fraction work. So now we've got a common denominator up top, right? And so this becomes 5 plus negative 3 over 2, all divided by 2. Well, this becomes 5 minus 3, which is 2, and then divided by 2. So you've got 2 over 2 over 2, which is just going to be 1 over 2. Right. So your baseline is at the half or 0.5 point mark. Y equals 1/2. So now we'll be able to find the amplitude, right? Because the amplitude is from the baseline, and so we need to know the baseline before we can find the amplitude. So now, to find the amplitude, I think it's the other way around. Yeah. We subtract the baseline value, baseline E, the baseline value from the maximum value. Need to change that. So A is the amplitude. Is going to be technically the absolute value of 5 over 2 minus 1 over 2. 1 over 2 is the baseline. So this is the max and this is the baseline. Because I'm doing the maximum, I don't actually need the absolute values, but it's not going to hurt.
You wrote that backwards, but the baseline subtracted. Should be the maximum subtracted.
We should subtract the.
Oh, that's right.
I know. We subtract the baseline value from the maximum value. I'm okay, right? Only because I copied it from the textbook and they had the maximum value from the baseline. But feeling pretty confident, actually. Yeah. So we've got a common denominator, so we can combine these. And I am showing way more steps than you would have to, right? But it's good to see them all. The gang's all here. The absolute value of 2, which is just 2. So our amplitude is 2. So now we can combine these to construct our formula, or to construct our equation, rather. Remember, we had our general formula was C of t equals a cos of omega t plus phi, and then plus b. So f of t is what we wanted. Our equation to be named. The amplitude we just found was 2 times the cos of omega we said was pi over 3 way back when. So pi over 3 times t plus 5, which was also pi over 3. Plus b, the baseline, which we just found was 1/2. And I'll put kind of big brackets around this cos, but it doesn't really matter. There. Did it. You would do the same thing if you had to do the sine one, but how about I'll leave that as an exercise to the reader, to the listener. And then I thought I was going to run out of time, so I actually decided to cut the last example. So we're all out of material for today. But, oh well. Let me just put it in here so that I can show you. And then I'll go back here. Leave as an exercise. Any questions about that though? So we worked forwards, we worked backwards. We were given an equation, we graphed it. We were given a graph, we made an equation. What more could you want?
So in that whole process though, we're really not even involving sine or cos until like the end when we construct our formula.
Yeah, they really only dictate the shape, right? So we're not doing anything with them. Yeah, cool. Any other questions, comments, concerns?
-3 over 2 and 5 over 2.
That's right. Nice. Cool. See you guys, I guess, on Tuesday. Make sure you do that Moodle quiz. It's due next Thursday, but give it a whirl for assignment 6.
Do we have all the information needed to do it now? Or is there
You do, actually. I think you did last day too, but yeah.
You really know.
I am.